In this video, we cover M-ary transmission. We'll study both the multi-amplitude case and the orthogonal cases. So the objective is to study M-ary communication. In baseband, we'll look at multi-amplitude and orthogonal signaling. The passband will be covered in the coming video. Now let's start by motivating the topic. Why do we go for M-ary communication? Remember the example we gave for different applications or transmission data rate. When you go from black and white images to high resolution colored images and video, the data rates start to increase dramatically. So new application call for huge data rate or high data rate, but we are limited in terms of bandwidth. We have physical channels. Now, what's the solution to this? We have two solutions. The first one is compression. We can compress the data, reduce the data size, but unfortunately, this is beyond the scope of our video. It's an important solution, but it's beyond our scope now. The second solution is to use M-ary communication. What does M-ary do? M-ary will expand the channel ability. We are limited by the channel, but by using M-ary communication, we kind of expand the channel ability to carry information. There are two types of M-ary. We'll cover both of them, multi-amplitude and orthogonal signaling. So let's recall the channel capacity theorem. There we learned that for a baseband channel, the channel capacity, the highest amount of data rate that you can transmit, is twice this bandwidth. For a given bandwidth, let's say 1K, you can transmit 2K symbols per second. But it doesn't say bits per second, it says symbols per second. What's the relation between symbols and bits? Because at the end of the day, usually we measure the data rate in bits per second. So the channel does not limit the transmission of bits per second, but it rather limits the symbols per second. What's the relation between the symbols and the bits is what we are trying to do with M-ary communication. So when using Gray's cosine, the relation between the bandwidth and the rate is given by the following. So this is the maximum when using sync, but if you want to be more practical, then there is also a factor of the role of factor R. If R equal to 0, we go to this limit, but if R is practical, we have R more than 0, so the data rate will even be less. So we are limited by this data rate. One thing we can do is to try to increase the number of bits represented by one symbol, so the bits per second will increase. And this is the trick behind M-ary communication. Now let's try to understand the difference between symbols and bits. Symbols versus bits. In the binary case, what we do, we transmit one of two possibilities. So either, for example, the following symbol, positive, or the following symbol. We have only one of two symbols to transmit. This is called binary. Binary, we have two. So every one of them, every pulse here or every symbol represent or carry one bit, either 0 or 1. What if we can send 4 possible levels? What we have 4 different symbols? We have 1, 2, or on the negative side, then we have also 4 different possibilities. Then we have 4 symbols, we can assign 2 bits at a time. For example, so binary systems, they have only 2 possibilities, 2 symbols. And in that case, a symbol equal to 1 bit. We're saying here, 1 pulse is equal to, or 1 symbol carries 1 bit. Now we can do better than this. In M-ary communication, it means we are going to communicate not with bind, not with 2, with M-ary, with M number of symbols. Like for example, in English language or Arabic language, which could have 26 letters or 28 letters, these are the symbols. In that case, if we have more than 2, it's called the M-ary, and the relation between the number of bits and the number of symbols is this. This is the number of symbols. If you take log to base 2, if the number of symbols, like here we have 4 possibilities, m equal to 4, you get log of 4 to base 2 equals to 2. So capital M is the number of symbols, Im is the number of binary digits per symbol. This is the relation between the two. The higher the value of M, the higher the value of Im, and in that case we get more data to be transmitted in every symbol. Now the bit rate becomes IM multiples of the pulse rate, and we need to generate M different symbols, or M different possibilities at a time for a given time slot. So in binary, symbol equal to bit. In non-binary, this is the relation that governs the two. I'm going to summarize this in a table. So you are expected to get this relation. Okay. The number of symbols equal to 2 raised to power im, or im equal to log of base 2, log of m to base 2. In that case, the bit rate is going to be increased. RS is what appears in channel capacity. RS is what's limited by the channel capacity. So we can increase the data rate, which is RB, bits per second, by scaling by IM. We'd love to have IM as large as possible. Now, before we proceed with M-ary types, different types, I'd like to make the following notes. First, binary is the single most important way for communication. And the reason is that in many cases we look for simple communication, like in toys and simple devices. We don't want to complicate things by going to a large number of symbols. So binary is still very important. But we use M-ary in application like satellite communication or wherever we have a limited channel and would like to get high data rate. So what are the types of M-ary communication? We'll classify them into one main type first, which is baseband without a carrier. And under that we have multi-amplitude, and then we have orthogonal, or multiple amplitudes, and orthogonal signaling. We'll cover this in the following video, in this video. And the second type is baseband. Even in baseband communication, we could have multi-amplitudes, multi-phases, multi-frequencies, or some combination between these two. So for now, we'll focus on M-ary baseband signaling. The first type of M-ary communication in baseband is to use multiple amplitudes. I'm showing the example here. If you'd like to have pulses, this is the time dedicated for a bit or a symbol now. It's not a bit anymore, it's a symbol. So I can send either this pulse, or the lower one, or the fourth possibility. So the difference between these pulses is in the amplitude, and this is why we call it multi-amplitude. I could have 4, and those 4 levels, the first level is A, the negative level is minus A. This is binary signaling. Since the spacing between these two is 2A, to keep the same spacing and the same probability of error, we have A minus A, the spacing between them is 2A. So to keep the same spacing between the levels, the next level will be 3A and minus 3A, not minus 2, because if it was minus 2, the spacing here will be just A. And then we have unfair distribution. And if you are sending this, it will have more probability of doing mistake. It will be closer to the lower level. And this is why we have A, 3A, minus A, and minus 3A. If you have this example of 4 levels, then you can send 2 bits at a time. 0, 0, 1, 0, 0, 1, and 1, 1. It looks in the sequence, your data will look like something like this: 0, 1, 1, 0, 1, 1, 1, 0, 0, whatever. It depends on what data you are transmitting. This is called multi-amplitude. The example of M equal to 4, 4-ary or quaternary is what we have just explained. And in this case, 2 binary digits can be transmitted by one 4-ary symbol. We're showing here that there is some spacing because we are using return to 0. So we're going up and then we're returning to 0, down, returning to 0. So the example shown is for the return to 0 case. Now to make, again, we just mentioned, to make the system is equivalent to the binary case in terms of probability of error, bit error rate, to some extent, we kept the spacing here of 2A. So this is why we sent A and then 3A, because the original spacing between the two was 2A, and this is why we're sending A and then 3A, minus A, minus 3A. Now let's look at the power, the average power for the case of the binary example. Either you send minus A or plus A. This is constant, assuming you are covering the entire time. So we get the power, the average power is either A squared or A squared, because the minus sign does not change the power. We divide by 2, assuming that the average, half of the bits will be 1 and half of them will be zeros. So again, the average power is A squared. Okay, and again, this 2, we divide by this 2 because we have 2 different possibilities. We sum them and we divide by the 2. This is the average power of sending pulses in the 2-ary example. What about the 4-ary case? In the 4-ary case, you can see here that we have a, so we get the power a squared, or 3a, 9a squared, or minus a squared, and then minus a squared, it becomes 9a squared. If you sum them up, you divide by 4, because we have, every time we have one of these 4 possibilities. The average power becomes 5a squared. It's the original a, we are adding 4a squared. You can see that the amount of power increase as we increase the number of levels is not just doubled. Okay. I would like you now, as an example of practice, to show that the power for the 8-ary case will be given by the following. It will be a squared plus 20a squared. This is a good practice, and you can share your comments below. What are the levels for the case of for 8-ary? A, 3a, 5a, 7a, whatever. Then you go down in the same way. You find the average power, and you should get 21a squared. If you don't, you are missing the point. So the power, although we are doubling the number of levels, the power is not just doubling, it's increasing dramatically. So this is important. This is important price for going to M-ary communication. Now, if somebody said, I'm not going to increase the power, okay, so I can send 4 levels and I can squeeze more levels in. So I sent 8 levels here and 4 levels here, while I did not increase the power to 3a, 5a, I'm just squeezing things in. What's the problem? The problem is that you get more probability of error. So it's not fair comparison in terms of power between these two, because we are not having the same power. Now, if you have a small amount of noise, it's surely not going to affect the 4 level case, but it could destroy the 8 level case. So if you want to squeeze to have the same power, you pay the price in terms of probability of error. Now, what is the limit? Okay, how many levels can we have? How many levels can we have in general? I'm showing you 2 examples. For the case of high signal to noise ratio, we have strong signal. The same noise is shown here. And we have low signal to noise ratio. I am showing this in terms of weak signal. This signal is shown here below as small amplitude. If you combine these two together, you'll find that the levels are distinguished. So we can distinguish between the levels. We have no problem. But once the levels are getting close to each other, you can see that we could mistaken the pulse from being negative into positive, and we lose things. So you have to make sure that when you add levels, the spacing between the levels is much greater than the noise. Otherwise, you start confusing the levels. And the signal to noise ratio is measured as the signal level divided by the noise power level. You can add levels as much as you can, but you have to make sure that you don't confuse the levels. The noise is not high enough to lose the signal. Example: how many bits are required to send 3000 bits using 2-ary binary system, 8-ary system, and 64-ary system? Okay, so in the question we are given the number of bits, and he is asking for the number of symbols. What relates the two together is Im, which equal to log base 2 of capital M. For the case M equal to 2, we get Im equal to 1. For the case of M equal to 8, we get Im equal to 3. And then we get Im equal to 64. It becomes 5. So this is the relation. You take this number and you divide by Im. So 3000 by 1, we get 3000. 3000 by 3, because this is what relates the symbols to the bits. We get 1000, and finally we get, 64 is 6. Okay, so you divide by 6, and you get 500 symbols. The second question says this. Consider this as a practice. It says, what is the average power required for 16-ary multi-amplitude case? We just have found the average power for the case of binary, and then we did 4-ary, quaternary, and then we did 8-ary. It was, if you remember, it was a squared, 5a squared, 21a squared. I would like you to find out what's the case of 16. Please share your answer in the comments, and let's see how many of us can get the same answer, and that's most likely is the correct answer. Now, in this slide, I'm going to summarize what is the payoff, what's the trade-off between going for high data rate. So I'm making this in terms of table. So I'm just looking at two cases. In the first case, if you go for multi-amplitude, increasing the amplitude is not supposed to increase the bandwidth. So going for m equal to 2 or 4 or 8, the bandwidth is fixed in both cases. How about the rate? Okay, the rate is, we can trade off here. We can see that if you want to fix the power, if you want to fix the probability of error and increase the rate by increasing m, then you have to pay the price in terms of power. Alternatively, if you don't want to say to increase the power, you fix the power, and you still want to increase m, increase the rate, multi-amplitude, then the price will be paid in terms of probability of error, because you cannot just keep the same levels. The levels will become close to each other, and then you lose in terms of probability of error. We can view the same table in a different way. Now, we notice here that the bandwidth is independent of m. The amplitude changes and does not, the duration does not change, because for pulse, what changes the bandwidth is the pulse duration rather than the amplitude. And this is good because the rate is increased by a factor of Im. I'm showing this with green. But we just say that the red part here, either you pay the price in terms of power. So the negative thing here, the cost to maintain the same probability of error, power increase is proportional to m squared. This is an important note here. So as you increase m, it's not linear increase in power. We have seen a squared, 5a squared, 21a squared, and so on. So the power increase is proportional to m squared. If you fix a, then we added 4a squared, then we added 20, so it's not linear relation. Okay, so alternative rate, another way to think about this, if you want to get the advantage in terms of bandwidth, you can say that I'm not going to increase the rate, I want to fix the rate and reduce the bandwidth. So rate and bandwidth are traded in the channel capacity equation, so we can fix the rate and then decrease the bandwidth. It's up to you. But again, the trade-off remains here, either in terms of probability of error or power. One will increase and the other will be fixed. So the lesson we learn here that this is an engineering problem where we have to get advantage and pay the price. Multi-amplitude does not come as a free lunch. Okay, so please you can complete this table as an exercise, and it's going to be similar to what we had before. Now, this is motivating us to the next slide. I don't want to get these disadvantages. So is there another way to trade off things? And the answer is using orthogonal signaling. Okay, I want to pay the price in terms of bandwidth. I don't want to pay the price in terms of power or so. So let's see what we get next. The second type of M-ary communication or M-ary signaling is the orthogonal signaling. We just finished the M-ary multi-amplitude, and now we look at orthogonal signaling. Orthogonal means we're going to send signals that are orthogonal to each other. So when do we call signals orthogonals to each other? We know that two lines are orthogonal to each other. If we draw the lines, one will be, for example, vertical or make a 90-degree angle with each other. But for signals, we say two signals are orthogonal if we multiply them and integrate and we get the answer to be 0. Then they are called orthogonal. So for a set of signals, phi sub I, within a range of time from 0 to to capital T sub b, within the duration of the bit. So 0 to TB is the duration of one bit. Now, if you multiply the two signals and you get 0, we call them orthogonal. So, of course, when I equal to j, it means we are comparing the signal with itself. So we get the energy of the signal, we get a constant. But when I does not equal to j, we are comparing two different signals which are orthogonal, so the answer must equal to 0. And here is an example. The following four possibilities, they are four symbols, but they are not multi-amplitude, they are all different from each other. And they are orthogonal, which means if you take this multiplied by this multiplied by that, and then you integrate, you multiply any two by each other, and you integrate, you get the answer always equal to 0. Of course, if you multiply the signal by itself and integrate, you'll get the energy of the signal. Now, if you use these four possible symbols, you get the example of capital M equal to 4. I'm showing another example with capital M equals to 8. So we have 8 different symbols which are orthogonal. This is in baseband. Now, if you increase M, if we increase the number of levels, assuming that we keep TB the same, then you can see that the power does not increase, assuming that we're using positive and negative. So the power is independent of how many different shapes we add here. The second thing, you can see that the bandwidth is now proportional to M, because this, as you start to increase, you have more changes within the bit duration. More changes means we have more bandwidth. So the bandwidth is proportional to M. Now we can build the following table. Okay, for orthogonal signaling, the power is not supposed to increase. We have fixed power. As we increase M, as we go for 4, we go for 8. What increases is the rate, because now we're sending 2 bits at a time. This represents 0, 0. This entire thing represents 0, 1, 1, 0, and 1, 1. Here we have 3 bits, 0, 0, 0, up to 1, 1, 1. So the rate will increase. Every one symbol will carry more data. Now, when it comes to the probability of error, okay, and the bandwidth. So, as I said, if you increase the bandwidth, you can fix the probability of error, because these are orthogonal. These are not similar to each other. And if you multiply them and you get 0, it means they are orthogonal. They are not in the same direction, like the 2 perpendicular lines. So, and this is why if you increase the bandwidth, you can keep the probability of error fixed. But if somebody says, no, I don't want to increase the bandwidth, I can have non-orthogonal, then of course the price will be paid in terms of probability of error. Okay, so you can pause this slide and think again about the table. So orthogonal in principle, the bar is fixed and the data rate is increased. Now the following table, we conclude with the following table, which compares the multi-amplitude with orthogonal M-ary signaling in principle. So multi-amplitude versus orthogonal. Multi-amplitude, the bandwidth is independent of M, because amplitude does not change the bandwidth. However, the power is proportional to M squared. For orthogonal case, the bandwidth is proportional to M, if you want to keep, of course, the probability of error, and the power is independent of M. And in this table, we assume that the probability of error is, we're trying to fix the probability of error. So this is why it's not shown in the table. Now, who uses this, who uses that, and why do we have 2 options? I'm just giving you the example. Use multi-amplitude when the bandwidth is at a premium. When you don't have a bandwidth as an option, it's very expensive, very limited, then you go for multi-amplitude because you don't want to increase the bandwidth. This is like in telephone lines. And we go for orthogonal when the power is at a premium, when power is very important, because you don't want to increase the power for going for a higher number of symbols. And this is like the example in space communication, because in space communication, assuming shuttles in space, they don't have power to waste. So this table summarizes multi-amplitude orthogonal, which are 2 types of M-ary communication. Thank you for your attention. In coming videos, we will be looking at we'll look at M-ary and passband, and we'll look at carrier communication. Thank you again.